Hello, today we will talk about the types of sequences. Last time we had also seen about some types of sequences like constant sequences, finite and infinite sequences. But today we will be learning about bounded, monotonic and convergent sequences. Let us just go with the first one, which is bounded sequence. If you remember, how do we represent sequences? We can represent them in the real number line since we are dealing with real sequences. This will give you a clear idea of what is happening if a sequence is bounded. Okay, so let us just say that this is the real number line, and suppose the sequence are in this way. Okay, x1, x2, maybe x3 is here, x4, okay, and so on. But okay, all the terms of the sequences, they don't cross to this side and they don't go to this side. Okay, that is, they don't approach infinity and they don't approach minus infinity. Okay, that is, they can be bounded by two walls. Okay, suppose this one and this one. Okay, the sequences, the terms of the sequences never crosses these two walls. When such a case happens, we will say that the sequence is bounded. Okay, these two walls that we are referring over here, they are in fact real numbers themselves, okay, which we will denote by k, and over here as minus k. Okay, sometimes, okay, you may be thinking, okay, that it is not necessary that this one will be minus k. Okay, it can be even a positive number. Okay, but it is always okay, because if you can construct a wall here, similarly you can even construct a wall right over here. It really doesn't matter. The sequence will still be called as bounded, even if you can bound them by one wall or two walls, or no matter how large the walls are. Okay, so you can even bound them here. That is why, okay, we can refer to this one as k and this one as minus k. Okay, in just to be clearer, okay, for example, you may have the sequence like this. Okay, 1, okay, okay, and then 0 maybe somewhere over here. For example, you may have something that looks like this, 1 and 2, and the sequence are all over here. Okay, then you can easily construct a wall right here. Okay, maybe 2.1 and 0.9, or you can even construct a wall, say, let's say 3 and minus 3. Okay, it's not according to scale, but I hope you get the picture of what is happening. As long as we can bound the sequence by two walls, on the right wall and the left wall, okay, then the sequence is called a bounded sequence. Okay, so what exactly is happening? If you remember that we were denoting sequences in this way, we were denoting them like xn. So you see over there that the terms of the sequences, they lie in between. They are smaller than k. Okay, because the k and minus k over here. So these terms of the sequence, they are all smaller than k and they are greater than minus k. So if such a case happens, then we will say that the sequence is bounded. Okay, with that being said, let us just give a proper definition. Sequence xn is bounded if there exists, and I should mention over here, real sequence is bounded if there exists a real number k such that minus k less than xn less than k for all n belongs to n. Okay, that is, x1 is Even if n is 1, it will be in between. Even if n is 2, it will be in between, because this is the set natural numbers. Okay, that is for all the terms of the sequences, xn, the terms lie between minus k and k. In fact, this one can be replaced by simply xn less than or equal to k. Okay, so we can write it in this way, or we can write it by using the modulus. It is the same thing. For me, I prefer to write it in the form of modulus. Then if required, I will expand it, this inequality, in this way. Okay, I will give examples later, or maybe I should give them now. Okay, examples. Let us say xn. Number 1, xn equal 1. Okay, if xn equal 1, then what do we have to do if we have to show that it is bounded? We just need to find a k such that xn less than or equal to k. Okay, if you remember, this sequence can be written as 1 1 1 1. Okay, if you expand this sequence, you can even write it like this. So all the terms of the sequence, if you take the modulus, it will be less than or equal to 1. Okay, so you can even take 2, it doesn't matter, but why choose 2 if you can choose 1? Okay, let us just try to choose the smallest. Okay, it really doesn't matter. We can even choose the biggest. Okay, we can even choose 2, 3, 4, 5, a very large number, even 1000. Okay, but why do that if we can do it with a small number? Okay, it's bounded since for all n belongs to n. Okay, now let us have a look at a sequence that is not bounded. Okay, maybe number 2. Xn equal n. If you expand this sequence, then you will be having x1 is 1, x2 is 2, x3 is 3, and so on. If you plot this one in the number line, you will see that it is actually increasing. Okay, you will be able to find the left wall, but you cannot never find a right wall. Okay, because if such a right wall exists, you can see that these terms actually keep on increasing. They will always cross a wall. Okay, no matter where you construct the wall, these terms will always go beyond that wall. Okay, so that is why it's not bounded. Okay, so this is what is happening. Okay, I will do some more examples later on when I'm doing the exercises. But as you see, this is exactly what we will discuss next. You notice that this sequence, you can construct a left wall, but you cannot construct a right wall. Okay, so that is why we can even define about number 1, okay, left bounded, or you can even call it as bounded below. A sequence is bounded below if there exists a real number k such that, okay, maybe m. Okay, m such that m, okay, it is bounded below, so that is why we will only have the left side of the inequality. Okay, we won't have another term on the right side. Similarly, you can define number 2 right bounded or bounded above. Okay, so we can even talk about this. So a real sequence is bounded above if there exists a real number m such that xn we can only construct the wall on the right hand side, but on the left hand side we cannot construct the wall. So xn less than or equal to m for all n belongs to n. Actually over here m, it is called as the upper bound, and that small m before, it is called as the lower bound. Okay, I forgot to mention, you can do it. Small m, it is the lower bound, and capital M, it is the upper bound. Okay, so with that being said, let us just go ahead with the next one, that is monotonic sequence. We will do some more examples later on. Okay, so if you remember, okay, we had actually encountered something similar when doing calculus about monotonic functions. Okay, monotonic increasing and monotonic decreasing. Similarly, we can have strictly monotonic increasing, strictly monotonic decreasing. Okay, so what is happening in monotonic increasing? If you plot it in the number line, you will have x1 over here, x2 here, x3, x4. Okay, so if it keeps on increasing in this way, then it will be called a monotonic increasing sequence. Whereas if the terms keep on decreasing in this way, okay, x5, okay, then this one will be called as a monotonic decreasing. Okay, and what happens actually, okay, we can even have strictly monotonic increasing and strictly monotonic decreasing, but the basic idea is this. Okay, I will define it properly. So the first one is strictly monotonic increasing sequence. Sequence xn is strictly monotonic increasing if, okay, how will we define it? You can see that over here x2 is greater than x1, x3 is greater than x2, x4 is greater than x3. So if x1 is less than x2, less than x3, and so on. Okay, but to write it in this way, okay, it takes too much time. Okay, so that is why we can easily write this one as xn less than xn plus 1. Okay, for all n belongs to n. Okay, this means the same thing as this. For example, x1 is less than x1 plus 1, which is x2, x2 less than x2 plus 1, which is x3. Okay, so we will be having this. Or we can even, if you take xn to that side, we will be having xn plus 1 minus xn greater than 0. Okay, for all n belongs to n. Okay, so you can define it in this way, or in this way. Okay, and do not forget the 3 dots. Okay, to indicate that it continues. Okay, similarly we can define strictly. Okay, what exactly we will define next? We will remove this strictly, and we will keep only monotonic increasing sequence. So a sequence xn is monotonic increasing. Okay, over here, what exactly are we having? If it is strictly, we only have less than, but over here it is less than or equal to. Similarly, over here, we can replace. Okay, so for the definition number 2 about monotonic increasing, the terms, they can even be equal. Okay, they can be equal. Some of the terms, they can be equal. Okay, and we will be having this. Okay, greater or equal, less than or equal to, greater or equal to. Okay, the third one, we can similarly define about strictly, okay, not same, it is strictly monotonic decreasing sequence. Okay, strictly monotonic decreasing if, okay, if it is decreasing, then all the inequalities will change. Okay, the first term will be the biggest term, then you can proceed in this way, and then the 3 dots, or we can even write it in this way, xn greater than xn plus 1 for all n belongs to n. It is the same definition, okay, like I had explained, or we can write it in this way, xn plus 1. Okay, if you move this one to the right hand side, you'll be having this less than 0 for all n belongs to n. Okay, so you can even define it in this way. Similarly, we can define number 4. We remove the strictly, and we can define only monotonic decreasing. It's just that now they can also be equal. Okay, so I will show examples. Okay, the first, okay, let us take a look at examples. Again, we will do more examples, but these are the basic examples that you will need to understand. Okay, number 1. Okay, let us say xn equal n. Okay, if you expand this one, you will be getting 1, 2, 3. Again, you notice that they keep on increasing, and the terms, they are never equal. So that is why this one, it will be strictly monotonic increasing. Okay, it is also monotonic increasing, in fact. Okay, because you must remember that this sign, it means less than or equal to. Okay, so even if it is just less than, it will hold. Okay, but more about this later. But just know that whenever a sequence is strictly monotonic, then it will also be monotonic. You can even think of it in this way. Okay, this one, you are having this symbol, so this one is also present over here. So that is why if this one holds, then this one also holds. In other words, if it is strictly monotonic, because this symbol is also present over there, so it will also be monotonic increasing. Okay, because this symbol is present. In fact, over here we have an additional symbol, which is equality. Okay, let's take a look at another example. Xn equal minus n. Okay, if you take a look at this, you will be having minus 1, minus 2, minus 3. So the terms, they keep on decreasing, so they will be strictly monotonic decreasing, and also it will be monotonic decreasing. Okay, let us see the third one. Okay, let's say xn equal 1. Okay, xn equal 1. Okay, so if you expand the sequence, you can write it as 1 1 1. Okay, but this one, it is actually monotonic increasing as well as monotonic decreasing. It is also constant. Because remember that in monotonic increasing, we were having xn less than or equal to xn plus 1. You also have the equal sign. Okay, this equal sign. So over here, they are all equal. So that's why it is monotonic increasing, also monotonic decreasing. Okay, number 4, another example. Okay, I will just write it in an expanded form. Let's say you are having this. So these terms, okay, if the pattern continues in this way, suppose they keep on increasing, then this one, it is not strictly monotonic, because if it is strictly monotonic, the terms cannot be equal. But over here, some of the terms, they are indeed equal. Okay, so that's why this one will only be monotonic increasing. Okay, similarly, you can have something that looks like this: minus 1, minus 1, minus 2, minus 2, minus 3, minus 3, okay, and so on. This one will only be monotonic decreasing. Okay, what about something that is not monotonic? 6. Okay, how about this? 1 2 3, okay, 2 1 4 5, okay, and then it continues. Okay, first it increases, then it decreases, okay, then it increases again. So that's why this one, it won't be not monotonic. Okay, it neither decrease nor decrease. So that's why it is not monotonic. What about number 7? Okay, in fact, this example is done. You can think of this one on your own. What if we write xn equal minus 1 power n? Okay, think about it. Is this one monotonic increasing, decreasing, or is it not monotonic? Okay, you can write the expanded form first. Okay, just find the terms of the sequence and then conclude. Okay, so this is about monotonic sequences. We will do more examples later on, but now let us just head over to convergent sequences. But before doing that, we must first define something which is called as the limit of a sequence. Okay, so before doing this, let us have a look at an example. Okay, let's say take this sequence xn equal 1 by n. If you calculate the terms, then you will be having x1 equal 1, x2 it's 1 by 2, x3 it's 1 by 3. Okay, if you calculate these numbers, okay, you will see that they keep on decreasing. Okay, similarly x4 equal 1 by 4, which is 0.25. They keep on decreasing. What is happening? So we start with 1, then we will be having 0.5, 0.3. Okay, but they will never be able to cross this 0. Okay, they will just approach this number 0, but they will never cross to this side. Okay, they keep on decreasing, starts with 1, keep on decreasing, never crosses 0, but they approach the number 0. In fact, you can even think of substituting n equal infinity over here. Okay, that is not valid. Okay, if n approaches infinity, then xn approaches 0. So over here, 0 will be the limit. Okay, so that is exactly what we will define. Okay, but if you remember, we had also studied about limit of a function. Okay, limit of a function at a point. okay, we had done it by using epsilon and delta. Over here also we will be using epsilon. Whenever limits are involved, you must know that you must use epsilon, okay, which I will define now. Okay, so we will be using epsilon to define about the limit of a sequence. So over there you were seeing that the limit of that sequence is 0. 0, it is a real number. Okay, the limit of a sequence xn, if it exists, okay, or we don't even need to write this one. The limit of a sequence xn is a real number x. Okay, some they use to denote it with L, okay, but I'm comfortable with using xn with x. Okay, depends, your choice, just a notation. Okay, you can use a different letter. It's a real number x such that for every epsilon greater than 0, there exists n belongs to n, so that xn minus x less than epsilon, okay, this is pronounced as epsilon, whenever n is greater than capital N. Okay, right now just take this one as it is. Okay, I will send another video that properly explains what exactly is this definition talking about. Okay, but for now just remember this. Okay, about the node, the limit is okay, so if it exists, there exists a real number x. The limit does not exist, okay, okay, the limit may or may not exist. I will write it in that way, may or may not exist. But if it does exist, it will be a real number. Okay, that satisfies all of these conditions. Okay, so how will we define a convergent sequence then? Okay, a convergent sequence is a sequence that has a limit. For example, okay, you can easily tell that 1 by n approaches 0, that is, it converges to 0. A sequence xn is convergent if it has a limit. That is, there is a real number x. Okay, we can write it there. That is, there is a real number x such that for all epsilon greater than 0, there exists n belongs to n, so that xn minus x less than epsilon whenever n greater than capital N. Okay, so this definition is very important. You will have to remember it. Okay, so these are the types of sequences that we are learning today: bounded, monotonic, and convergent. About the proper explanation of limit and convergent, I will do in the next video. But now, okay, let us just have a look at some examples of convergent sequences. Okay, based not on this definition, but from our intuition, from our understanding only. Okay, without using the definition. Okay, let us take a look at this. Okay, number one, let's say xn equal n. Okay, then if you expand this one, we have been doing it many times, you will be having this one. So this one, it will approach infinity. All right, if you keep on calculating it, it will get bigger and bigger. So we say that it will approach infinity. So that is why infinity, it is not a real number. That is why the limit does not exist. Okay, so not convergent. Okay, number 2, let's say xn equal 1 by n. Okay, we had seen that this one, okay, we had only get an idea from the picture, okay, and from calculating. Okay, we did not use a definition. Okay, but let us just go ahead with it, that this one approaches 0. 0 is a real number, so the limit is 0. So it is convergent. Okay, let's take a look at this one. Xn equal minus 1 power n. Okay, if you expand this one, you will be getting minus 1, 1, minus 1, 1. Okay, it doesn't approach a fixed number, okay, because it keeps on oscillating. Okay, from minus 1, it changes again to 1, and then the next step again it changes. It keeps on repeating this pattern, keep on oscillating. So that is why, okay, the limit does not exist. So not convergent. Right, so with that I end today's video.